What is the one fact about the universe that blows your mind the most?
There are a lot of things about the universe that I find it almost impossible to imagine. One is just the size and scale of it. I mean, in the piece of the universe we can see, there are something like 2 trillion galaxies.
Picture this. A vast black space twinkled with billions of stellar nurseries, twirling 8 giant planets, 200 billion trillion stars, 171 divine moons, 3,881 well-known comets, 8,000 cutting-edge satellites, and millions of asteroids. Can you imagine how this giant space is home to these trillions of celestial bodies? And that's just the beginning. There's so much more horizon that's still under the sheds. From the earliest bang to today's leading astrophysicists, the universe has always been a source of wonder and intrigue. If you dig further, you find yourself delving into the heavenly cosmos of quantum entanglement, supermassive black holes beyond beautiful nebulas and whatnot. The universe somehow feels like an unsolved puzzle. How, when, and where it's come from and exploded into such a giant is a no-brainer. Even if you want to ponder about it, you can't. The mystery is fascinating but overwhelming as well. And the cherry on top is, it's the same everywhere. You'll encounter similar conditions in every corner, be it the homogenized temperature, its flat shape, or whatever. It's not like the universe doesn't change. It surely does, but not as we think. It's constantly evolving. Like 13.8 billion years ago, the universe began as a singularity, a point of infinite density. But now it's super big, supermassive, and home to trillions of celestial bodies. If you love wandering, think of star cycles, galactic evolution, dark matter, dark energy, and evolving cosmic structures. And imagine how these planetary objects have one pattern, an undying similarity, though they are still evolving. However, if you can't wonder enough but love to venture into a virtual cosmic voyage, watch this video till the end and see how the universe never ends but is the same at every freaking corner. Let's talk about cosmic strings first. If I put it simply, these strings are flawed. A crack, a defect in the universe, and even considered hypothetical most of the time. If they really exist, these cosmic strings must have been born in the universe's earliest days and probably helped explode it into such a supermassive space world. When the insane energies were disrupting the universe like a Hulk, it distorted space-time and twisted it to the extent that it left permanent scars, simply wrinkles that we're calling cosmic strings today. The strings are impossibly thin, no wider than a single proton, but packed with such power you couldn't even imagine. Only a mile long, these cosmic strings would weigh more than the entire planet Earth. Now this is just insane. How can such a size mass weigh more than Earth? It's a no-brainer, an absolute hulk to even think about. Well, let's move forward. Despite their thin structure, they are incredibly dense and move closer to the speed of light, resulting in gravitational repulsion and waves in the fabric of space-time. Just like the cosmic string, there are also superstrings that exist in the universe. Superstrings are said to belong to the realm of the quantum. They are fundamental objects in string theory, a theoretical framework that describes the universe's fundamental forces and particles, considering them tiny, vibrating strings of energy. However, they don't have the structure of cosmic strings. Superstrings are relatively tiny, on the order of the Planck length, that is exponent 35 meters, which is many times smaller than an atomic nucleus. However, both these strings are said to play a significant role in the formation of the universe. They could be the reason why the universe is still well-balanced and potentially similar everywhere. Cosmic strings, being massive bodies, extended a strong gravity pull on the surrounding cosmos. This could have led to the formation of galaxies and galaxy clusters along these strings, creating a cosmic web with strings as its backbone. Similarly, superstrings are also somewhat playing the same role. They are said to have been in existence before the universe was just an inception, nothing real. Can you believe this? Well, the scientist also says the vibrational modes of superstrings have influenced the universe's initial conditions, setting the stage for the subsequent formation of particles, forces, and the very structure of space-time that leads to the uniform pattern of the universe. You may know how overwhelmingly the universe is stretched without a constant end, but with all its vast grandeur, there's a limit to what we can see and study. This limit defines what we call the observable universe. The observable universe is said to be 13.8 billion light-years old. We can only observe objects whose light has had time to reach us in that span. This creates a cosmic horizon beyond which we cannot see. However, you might be wondering how the universe is exactly the same everywhere and what the heck the observable universe has to do with it, right? The concept of universe uniformity is called the cosmological principle, and the observable universe has given numerous shreds of evidence that you can't deny, not a single time, I can bet. But before this, let's talk about the tools and techniques that are used to observe the light-years-away cosmos. Scientists use telescopes like Hubble Space, JWST, and OAO to get breathtaking images of distant galaxies, nebulae, and star clusters. Instruments like the Wilkinson Microwave Anisotropy Probe and the Planck Satellite have been crucial in studying cosmic microwave background radiation, giving us a glimpse into the universe's state shortly after the Big Bang. By using these instruments, evidence can be found. First up, let's see the CMBR, that is Cosmic Microwave Background Radiation. It's basically the afterglow of the Big Bang, and takes us back to when the universe was just 380,000 years old. Scientists use the Planck Satellite or the Wilkinson Microwave Anisotropy Probe and astonish the astrophysics that the temperature is evenly uniform in all directions, with only tiny fluctuations. You see how it supports the unchanging nature of the universe. However, the tiny fluctuations in background radiation are believed to be the seeds of the large-scale structures we see today, like galaxies and galaxy clusters. Secondly, when astronomers deeply studied the structure of the universe, they found it somehow web-like, never-ending body with hundreds and thousands of galaxies and its clusters interconnected by filaments of dark matter, forming a cosmic web. But guess what? Not at a single freaking corner, there was an uneven distribution of filaments. Its overall structure and distribution appear to be the same in every direction we look. That's just astonishing. However, the shreds of evidence certainly do not end here. There are so many more witnesses, but now let's delve into what the Big Bang says about the undying similarity of the universe. Who doesn't know about the Big Bang? It's the cornerstone of modern cosmology, a narrative of creation, evolution, and the intricate dance of matter and energy. But with time, this theory has also been revisited a long time. Once, what scientists used to assume was that it was a giant blast that resulted in a big-ass universe is not what modern astrophysicists believe. In 1920, the scientist, Edwin Hubble, made a groundbreaking observation. Distant galaxies were moving away from us, and the farther they were, the faster they were moving away. What do you think this theory says? It was a hell of evidence that the universe didn't stop, but it kept on expanding. However, the expansion happens systematically. It's not like one part expands and the other keeps constant. No, each corner of the web-like structure has expanded uniformly ever since. If the universe's expansion were not consistent, it would imply variations in its properties in different directions. The cosmic microwave background radiation is also considered one of the biggest pieces of evidence of the Big Bang explosion. As we discussed earlier, it's an afterglow snapshot of this massive explosion when the universe was just 380,000 years old, but the temperature has been homogenized since then. You may also notice the abundance of some elements in our universe, like hydrogen, helium, and traces of lithium. Prior observations show that these elements have always been greatly consistent. And so this uniformity in elemental abundance suggests similar conditions and processes in the early universe everywhere. But if it provides excellent evidence of the universe's uniformity, it doesn't mean it has no challenges and inconsistencies. As much as the CMBR is supposed to have an even temperature, There are some regions that are now widely separated and should never have been in causal contact due to the billion-year-old age of the universe and the speed of light. This is quite perplexing since the Big Bang is old for sure, but not this old that the light wouldn't have traveled in those areas. Also, the universe is flat. No curve, spherical, round, or any other shape owing to its incredibly dense properties. Thus, if any slight fluctuation had occurred in the early universe, it would have led to a vastly different density today, either collapsing back on itself or expanding too rapidly for galaxies to form. Not only this, the uniformity of the universe also gets questioned at another place. The universes should have the same amount of matter and antimatter. However, we observe a universe dominated by matter, and so this asymmetry is not fully understood. Not only this, but the concept of dark matter and dark energy also clashes with the uniformity of the universe. These dark entities are said to make up 95% of the universe's content, and their nature remains one of the biggest challenges in cosmology. But it's probably hard to look for their evidence in the Big Bang theory. Next up, let's talk about the quantum entanglement of the universe. Quantum physics has had a huge mental toll on scientists ever since it was made public. Not only does this theory challenge your prior misconception, but it makes things even more perplexing at the edge of the universe. Even Einstein couldn't resist calling the entanglement spooky action at a distance. It basically tells the merging of two particles in a way that the state of one particle heavily depends on the other, no matter how long or short the distance is. This means that if you measure the state of one particle, you instantly know the state of the other, even if they are light years apart. This nature typically defies classical notions of locality. The quantum entanglement is big times related to the massive Big Bang. The universe's birth in the Big Bang was an event of unimaginable energy and density. At such extreme conditions, particles would have been in close contact, allowing for far-spread entanglement. This much you couldn't put into perspective. Once the universe expanded, these entangled particles would have moved apart, potentially leaving a cosmic web of entangled particles stretching across the universe. Just like that, black holes also come into the film and are also related to this puzzling entanglement of the particles. Its enigmatic nature, especially the paradox of information loss when matter falls into a black hole, has led physicists to explore the role of entanglement. According to Juan Maldacena, the concept of ER is equal to EPR suggests that wormholes between black holes might be explained by quantum entanglement, linking the two seemingly disparate concepts. Simply put, wherever perspective you delve deeper, quantum entanglement seems to play a big part in the coherent nature of the universe. It talks about the deep layers of interconnectedness between the web-like structure. If particles that were once in contact during the universe's early moments became entangled and then were separated by cosmic expansion, it suggests a level of coherent nature and uniformity throughout the expansion ever since. Also, if the early universe had been really involved in entanglement, it's possible that the regions that are separated now might have remembered their old origins. This could lead to a level of uniformity and consistency in the universe's structure and behavior. However, it's also worth pointing out that the phenomenon of entanglement is universal. They apply everywhere, from the tiniest subatomic particles to the vast cosmic scales. This coherency of quantum principles supports the idea of a universe that runs on the same fundamental laws everywhere. Now, let's see what black holes have to do with this similar nature of the universe. You might think that's just a vast, empty, and dark hole in the universe, but hell no, it's more than what you think. This black hole has helped us test Einstein's theory of general relativity, which describes how mass, space, and time are related to one another. They are a particular region in space-time where gravity pulls so intense that even light doesn't dare to venture through it. The boundary surrounding a black hole is called the event horizon. Anything that crosses this boundary is inexorably drawn into the black hole, never to return. But how do they imply the universe is the same every freaking where? Let's get through it. You may know about supermassive black holes. It's found at the center of most galaxies, including our own Milky Way. These black holes have masses ranging from millions to billions of solar masses. Scientists say that black holes are a common feature in the centers of galaxies across the universe. Their back-to-back, or you can say consistent presence in such diversified galactic conditions says about the universal mechanism or set of conditions for their formation and growth. These holes prove the laws are universal. The universe is following the same conditions at every corner, no matter if it's billions of light years apart. Black holes also play a big part in regulating star formation and shaping galaxy evolution, suggesting that they have a consistent influence on cosmic structures. Whether you see their effects on their host galaxies, from radiation feedback to gravitational interactions, everything will appear universal, no matter what the conditions are. Black holes also talk about how these waves, ripples in space-time, are consistent with predictions and have been occurring billions of light years away, suggesting similar processes happening throughout the universe. Despite the black holes being the witness to the coherent nature of the universe, it also said to influence the formation of the galaxy. According to scientists, black holes' massive gravity pull is what keeps the stars and other celestial bodies in their respective orbits. Black holes also accrete gas and dust from their surroundings. They release enormous amounts of energy in the form of radiation. These radiations basically sizzle up the surrounding environment and prevent them from getting cool and supporting the birth of new stars or stellar bodies. This regulation by black holes greatly helps control the rate of star formation in galaxies. Also, when two galaxies collide, their central black holes can merge to form a larger black hole. This process results in the release of gravitational waves and can trigger bursts of star formation, influencing galaxy evolution. However, up till now, you may assume the universe is a flat 1D body, and that's the truth. But you know what the holographic theory says? It supports the idea that the universe might be a 2D hologram projected into a 3D space, challenging all the studies we previously did, and even kicking out all the perceptions we once said were reality. First, let's see what this holographic hypothesis says about the uniformity of the universe. Consider the small piece of holographic film containing information about the entire 3D image. Every part of our universe, under the holographic principle, has exactly the same information about the whole. Did you get what this says? It tells us the deep layers of universe interconnectivity are consistent throughout the universe, which means the universe is coherent and has undying similarities. However, if all the information in a volume of space is encoded on its boundary, the density of information is homogeneous. This hints at how precisely nature has made the universe consistent. Apart from this, the holographic principle came into existence from the study of black holes and string theory. It was then suggested that data on a surface or boundary may be able to describe all the information within a given volume of space. Enough about holographic films. Let's see what you know about the mystery of antimatter. Consider it as a matter twin. Every particle in the universe comes with its twin particle, which is known as an antiparticle. For example, the antiparticle of an electron is a positron, which has a positive charge. Similarly, the antiparticle of a proton is an antiproton. That's the law of nature, more precisely, the laws of physics. Though the twining of matter doesn't occur simultaneously, it comes into existence through the annihilation of matter. This annihilation produces photons, and the energy released is consistent with Einstein's famous equation E is equal to mc squared. The apparent imbalance between antimatter and matter is one of the significant research areas in the study of the cosmos. The Big Bang is supposed to bring an equal amount of matter and antimatter into the universe. But when you observe it closely, you may find the universe is mostly dominated by matter, unlike what the theory says, though it's a blessing in disguise. As if there had been equal antimatters, they would have annihilated each other entirely, leaving behind a universe filled only with radiation. Yet, here we are in a universe filled with galaxies, stars, planets, and life. The asymmetry in the baby universe is surely oblivious, but what in nature is useless? there must be true facts that are yet to be found. However, the antiparticle also implies the universe is the same everywhere. The dominancy of matter over antimatter has created a uniform pattern. Whether we look at distant galaxies or the cosmic microwave background radiation, we see signs of matter's dominance. This coherency shows that no matter the antimatter-matter asymmetry in the early universe, it was very universal in nature and affected each region of space equally. Next, we've got the multiverse theory to discuss the same nature of the universe. Have you ever wondered if the universe we're living in is just a comma? Maybe there's an infinite number of more worlds we never dare to think about. This idea is the basis of the multiverse theory, a concept that challenges our understanding of reality and creates an infinite universe. This theory says our universe isn't something oh so wild or pretty unique, but it's just an ordinary world amongst plenty of other universes. I know this sounds a bit awkward, but it's the reality in the making. It is part of a vast ensemble of universes, each with its own set of physical laws, constants, and properties. One universe may separate from the other at a billion light-years distance, or by such huge dimensions we can't perceive. Hold up! You must be thinking about what multiverses have to do with the coherency of our universe. I bet it's where things get more exciting. Just like our universe appears homogeneous and isotropic, with the same laws applying everywhere, this could be a feature of all universes in the multiverse. Each universe may be potentially different from the others. It would have its own set of consistent laws and properties. Simply put, uniformity isn't for our universe, but it's for every freaking world existing beyond that. You may also know about the enigma of dark flow and dark matter. That's not something super cool, new, and exciting. It's been in the universe since its birth, but its invisibility is what makes the scientists go crazy. These unseen forces and entities challenge our understanding of the universe and hint at the cosmos we never thought about. Talking about dark flow, it's quite an obvious motion of galaxy clusters moving in a coherent way in a specific direction at immense speeds. This mysterious dark flow was first made to the public through observations of the cosmic microwave background radiation, the afterglow of the Big Bang. However, let's first find out how it implies the universe is the same everywhere. Both dark flow and dark matter, despite their perplexing nature, talk about a level of similarity in the universe. Firstly, the very fact is that galaxy clusters that are interconnected with the universe's web-like structure have the same flow motion, and you know what it means. Our universe has a level of uniform influences, and similar motions and forces affect the vast region in an equal ratio. Also, dark matter makes up 27% of the universe. It particularly influences the rotational speeds of galaxies to the gravitational lensing of light, and all this phenomenon can be consistently observed in the cosmos. The presence of dark matter indicates that, at its core, the universe works under similar principles and is affected by similar forces. However, the origin of these dark entities is quite puzzling to think about. Some scientists say dark flow could be the result of massive structures, perhaps other universes or vast regions of matter lying beyond the observable universe's boundaries. But the other says this dark entity could be a remnant from the early universe, or might come into existence after certain fluctuations in space-time shortly after the Big Bang. Now, only nature knows what's the real truth. Apart from this, you might have probably never heard about wormholes. No, they're nothing as perplexing as quantum mechanics, but are quite simple to understand. Wormholes are described as tunnels or bridges through space-time. It helps us equate those pretty complex general relativity equations that suggest the existence of shortcuts between distant points in the universe. Its capability to solve those mathematical queries implies laws of physics are consistent throughout the universe. No matter if one planet is near the black hole or the other is in the intergalactic void or near a wormhole, the principles are the same. The laws of physics remain constant. There's no change in the fundamental phenomenon, and that's what heavily suggests that the universe is same everywhere. Wormholes also suggest that the universe is interconnected in its web-like structure. It's connected in a way you cannot perceive, but those distant regions that might be a billion light years away are connected by these shortcuts, indicating a level of cohesiveness and unity. If these bridges of space-time can exist, it's a clear indication that similar structures could exist elsewhere. This universal phenomenon, from wormholes to giant galaxies, hints that the universe runs under the same set of rules and structure. However, those wormholes are literally very exciting. This greatly reduces the light-year distance between distant stars or galaxies. It seems like interstellar travel will likely be introduced in a few years. Once was completely absurd even to imagine. Even wormholes could take one back to the past, or propel one into the future, time traveling. These distant bridges are going to revolutionize the space world much beyond what you could ever imagine. However, the concept of time travel is fully skeptical. The scientist doesn't believe in such a conspiracy, while some astrophysicists are sure that such a thing could exist. Not only this, but some theories also say that wormholes can be those bridges that help us to travel into another universe. As such, they may provide a means of exploring the multiverse. So, that's a wrap. With all those theories, you may know why our universe is the same everywhere. It is homogeneous. It has the same nature. Its web-like structure interconnects all the galaxies and stellar bodies the way that there's just equality in all the laws of nature and physics. Hit that subscribe button and let us know your opinion on the unchanging nature of the universe.